Okay, so thank you for being here. I'm Carlos Miguel Patiño, and today I'm going to talk to you about how to use Python to simplify statistical inference with probabilistic programming. So a little bit about me. I'm a physicist from Uniandes, and I'm currently working as a machine learning engineer at Factor. Factor is a company, part of the AI fund, and our mission is to help companies develop custom AI products quickly. We currently have clients in Colombia, Latin America, and also the US that range from small startups that don't have AI teams to large organizations that have hundreds of employees and honestly awesome AI and data science teams. In both cases, we either are their AI team to develop their product, or we reinforce their existing team to develop their AI ideas and products much more quickly. I'm also a member of the Deep Skies community. The idea with this community is apply AI knowledge to challenges in astrophysics. So that's enough about me. With this talk, I hope you learn basically three things. What is probabilistic programming in the first place? Which problems are best solved with probabilistic programming? And third, and this is going to be the main focus of the talk, where to start with probabilistic programming for your own projects. So with this in mind, this is what I'm going to cover in this talk. First of all, the definition of probabilistic programming. Second, why is it useful? Kind of a bit theory approach. A brief review of the probabilistic programming frameworks we are going to use in this talk. But as I told you, the main focus are going to be the examples. So the first two are kind of the hello world to the probabilistic programming. They're simple approaches, but really are important to know what we're talking about. And the last two are going to build on the first two examples, the more real case scenario. Okay, so let's begin. First of all, what is probabilistic programming? Because it's kind of a vague idea. What is probabilistic programming in the first place? So basically, in a nutshell, probabilistic programming is a framework that allows us to define and work with random variables. So for instance, in your model, you have a variable x1 and a variable x2. You want to apply a function to these two variables and get an output y. Okay? But since these functions are random variables, they have to be governed by probability distributions, right? So in this example, we have a normal distribution for our x1 and exponential distribution for our x2. And this is key because the center of probabilistic programming is actually modeling probability distributions as Python objects. And we will see in a bit why is it useful to develop models, probabilistic models. Okay, so this is what's probabilistic programming in a nutshell. But now let's focus on why do we want to do probabilistic programming. So basically, imagine you have a problem when, first of all, you want to encode prior knowledge of the problem. Either you have some expert in your team, you're talking to a client, and you want to encode this previous knowledge of the problem into your model, right? So that's the third thing. And also, you want to calculate an intuitive uncertainty of our estimations, right? So these are the key two elements, intuitive uncertainty and prior knowledge. And many of you may recognize this framework. This is the Bayesian framework of statistics. Right, so we are going to focus on this framework. For those of you who haven't heard about this framework, it's summarized through a Bayes theorem. Basically, the Bayes theorem has four elements. Okay, first of all, the prior, and this is where you encode the previous knowledge of the problem. You're saying when you're creating your model, this is what I know about my parameters. Please, this is my previous knowledge of the world. Okay, so through a prior, we are going to encode our previous knowledge. Second, we have the likelihood. Basically, the likelihood is given this belief of my world, I gather some data, and the likelihood tells me how likely is my data given the parameters I'm assuming. Okay, so it's kind of the relationship between my parameters and the real world. The third element is the posterior distribution. So basically, the posterior distribution is my updated knowledge given the data. So I began with a prior, with what I thought my real world is. I got some data and I updated my knowledge. Okay. And this is, in the posterior distribution, is where we encode the uncertainty of our estimations, okay? Since this is a probability distribution, we have a notion of uncertainty. So notice the encoding of a previous knowledge on the prior and the encoding of uncertainty on the posterior. The fourth element, it's called in many ways, but it's the evidence. And what's important about the evidence is it's difficult to calculate analytically, sometimes even impossible to do it. So we're going to focus on problems, and this is cool. This is what is cool about probabilistic programming. It allows us to calculate this posterior probability, this updated knowledge of our world, without taking into account the evidence term. So this impossible calculation is made possible by probabilistic programming. Okay? So basically, since we take the evidence out of the picture, we only need the prior. I mean, this is information we got because this is our prior knowledge of the world, and the likelihood, how our parameters relate to the real world. And with these two elements, we calculate the posterior. So we are going to focus on this kind of the characters of our story. Prior, likelihood, and posterior. We take the evidence out of the picture. And this is great about probabilistic programming because what are we going to do? Gather the data, our relationship to the real world, and define our model, okay? And once we do that, we use what Thomas Vicky, some core developer of PyMC3, calls the inference button. So the idea is you push the inference button when you have the data in your model, and the methods implemented in probabilistic programming calculate your posterior distribution. So this inference stage is totally implemented in probabilistic programming, and we will see the methods in a bit. Okay? So, just to summarize, why is probabilistic programming useful? It basically encodes, it lets us use the Bayesian framework, encoding prior knowledge and uncertainty. The second point is what I find actually most useful, because you are the one who is building the model. So you are the one who's defining the parameters, how the parameters relate to each other. So it's kind of an open box model because you know exactly what each parameter means in the model. And we will see why that's useful. And also the third thing is you infer the parameters. So you have your model and you push the inference button, and you have the values of your parameters with uncertainty. Okay? We are all Pythonistas here, so this is how the probabilistic programming framework would look like in a pseudocode on Python. We, the humans, are the ones who define our model. From the real world, we have the data, and from probabilistic programming, we have the inference button. So the model we define has parameters, and we tell to the inference button, okay, given the parameters I defined and the data I gathered, infer my parameters. And we would pass these assertions because the inferred parameters include the uncertainty because these are probability distributions, and the model includes our prior knowledge because we are the ones who define our model. Okay, so kind of a pseudocode about probabilistic programming. So the frameworks we're going to use in this talk are two, particularly PyMC3 and Pyro. There are more frameworks, but why did I choose these two? Because they kind of approach the problem of probabilistic programming from two different approaches. First of all, we have for PyMC3, it focuses on Monte Carlo methods. And the basic idea of Monte Carlo methods is to approximate the posterior distribution through sampling methods, okay? Contrary to variational inference, that it's the strength of Pyro, that it approximates posterior distribution through optimization. Okay, so basically two different approaches to the same problem, and we will see what each does in a bit. Each approach strengths and weaknesses. Monte Carlo methods are good for small data sets, and the good thing is we can guarantee an exact inference for our parameters when we use Monte Carlo methods. But the con for this is it's slow to do inference with Monte Carlo. On the other hand, we have variational inference. It's good for large data sets, but we can't guarantee that we have an accurate or exact inference. The pro is that it's fast, okay? So notice a trade-off there between those two methods. So the hello world example, both in probabilistic programming and in probability, the coin toss. So we will build from this to more complex examples. So we want to determine if the coin is biased, the classical example. So the coin is biased if the probability of getting heads in a single toss, it's different from 0.5. This probability, we're going to call it theta. This is the single parameter of our model. And remember, we need the model, the parameters, and the data. So we record a number of tosses to determine if the coin is biased, okay? So just as an example, and just between us, we know the coin is biased, a priori, as an example. So the probability of getting heads, we know it's 0.4. That's how we generated our data. So we know theta, it's 0.4, okay? So this is a model in probabilistic programming. Notice there's no Monte Carlo methods, Metropolis Hastings in the code. You just focus on defining your model, okay? We define it through a Python context. This is PyMC3. And what we do is define a probability distribution, a prior. In this case, it's a beta distribution. It's equivalent to a uniform distribution. So basically, we are claiming we know nothing about the parameter, right? Every value between 0 and 1, it's equally likely. That's the first actor of our model. And remember, the likelihood is how the parameters relate to the real world, right? So my single parameter, theta, it's actually modeling the real world. What is my real world? Two scenarios, okay? So is it heads or is it tails? Just a binary outcome. And which probability models these kind of scenarios? The Bernoulli distribution. That's why we use the likelihood as a Bernoulli distributions. And notice in the definition of y, we have an observed parameter, right? So we're letting the model know we gather some data. These are the tosses. Please use this as the data to update my knowledge from the prior, okay? And the inference button. So notice PyMC3 does this under the hood. We say to the model sample, some samples, Monte Carlo samples, in this case 5,000. That sounds like a lot, but it takes less than a minute to run. And the result is the theta parameter. So just to recap, in the orange box we have, we have the model we're defining, the parameters, the priors. We push the inference button, and the result is the theta value that we want to calculate. Okay? So let's see what we got. So is the coin biased is our question. So here are the plots for 10 tosses, 100 tosses, and 1,000 tosses. And I'm showing you the results without the uncertainty to let you know the importance of uncertainty. So notice the first plot, right? We have only 10 tosses, and the map, that is the maximum a posteriori, it's kind of the point estimate we want to use if you want to report the parameters. It's 0.5. So if we run the experiment, and with just 10 tosses, we would conclude incorrectly that the coin we're using is a fair coin, because this is what the model is telling us. But what about if we consider the uncertainty, okay? So notice the distribution of the theta parameter, it's very wide when we have a small data set, and it increasingly narrows when we get more data. So notice we have a more detailed analysis now. Since the distribution is wide, I cannot certainly say it is a fair coin for the first case, because the possible values for theta are less than 0.2, more than 0.8. I basically have no idea what theta is, right? Compare it to the last plot in this slide. We have a narrower posterior distribution, and what's more important in this one is it doesn't overlap with a value of 0.5 for the fair coin, okay? So we basically can say with certainty that this isn't a fair coin. And why? Because the distribution doesn't overlap with the value for the fair coin. So notice the importance of uncertainty in our measurements, okay? So now the second hello world example, the linear regression. And I wanted to use a real data set to encourage you to drop using, I don't know, the Boston housing data set and Iris data set, and start using a real world data set. I'm using results for Saberonce, for those of you who don't know it. It's an exam that people take in Colombia when they're graduating from high school. And I downloaded them from the open data portal for the Colombian government. There are thousands of data sets there for those who are curious. So this is the data set we're going to use for this example. So basically what we're going to use is model the overall score of the test based on the natural size score of the test. So we have the input x and the output y, and we have three parameters of the model: the intercept alpha, the slope beta, and the noise parameter epsilon. Okay, so 3 parameters, remember. And since we're taking a probabilistic approach, we don't have a point estimate, but we have for each point a distribution. It's a little bit different, but notice it's almost the same. The key thing here is that our mu for the normal distribution is what we consider a usual linear regression, but it stays the same mostly. Okay, so let's go to PyMC3 and let's build our model. So remember, three parameters, so we define 3 priors, alpha, beta, and epsilon, okay? That's it, we defined them. And the likelihood, as before, remember the relationship between the parameters and the real world. Our real world here is a linear regression model, so that's the one we defined in the last slide. But what I wanted to convey in this slide, remember the first slide of the talk. Random variables in probabilistic programming are objects. So notice I define basically probability distributions, a normal distribution, a half-Cauchy distribution, and here I'm adding them. I'm multiplying them to a Python array, here beta times x. So notice I'm treating them as basic Python objects. So that's the key for probabilistic programming. Notice you can do whatever you want with probability distributions. In the case you were dealing with pure Python, it would be very difficult to implement this kind of modeling, okay? And as before, we push our inference button, we sample 5,000 samples. Okay, that was with PyMC3. I wanted to show you the linear regression with Pyro. And it's a little bit more verbose. For those of you who have used PyTorch before, sorry, this should look pretty similar, pretty familiar. But notice the code between PyMC3 and Pyro for defining the model, it's similar. We define our priors with probability distributions, and we define our likelihood pretty much the same. We pass the data as an argument. But what's different between the 2 approaches is how we infer the parameters, right? Notice that we don't have a sample function here anymore. Instead, we have an optimization procedure. So let's walk through it. First of all, we have to define kind of a guide. PyTorch documentation calls it a guide. What's the guide? The distribution that will approximate the posterior by adjusting the parameters of the model, right? So you define kind of the object you are going to optimize by tweaking the parameters to approximate the posterior distribution. How are you going to optimize it? Through some optimization objects, Adam optimizer, for those of you who work in deep learning, it's completely equivalent. And the stochastic variational inference object, the SVI object, that it's equivalent to gradient descent on deep learning. It's the way we're going to update the parameters to approximate the posterior distribution. So these are our optimization objects. And as the same as in the deep learning approach, we have an optimization loop. We have defined the number of iterations. And through the stochastic variational inference, we update the parameters until they converge to the posterior distribution we want to approximate. So notice a very different approach to the sample function we used earlier in PyMC3, but they're equivalent to approximate the posterior distribution. The result, this is a hello world example, but I wanted to show you. Notice in the left we have a usual linear regression, right? So we fit our data, but in the right we have the result with a confidence interval calculated by the posterior distribution. So here we have a 95% confidence interval. We can say to the person who's using our model, we guarantee that our samples are going to fall within, 95% of our samples are going to fall within that range. So notice we have the uncertainty calculated, okay? So moving on to more building on those previous examples, I wanted to show you an example for the hierarchical model. And this is a scenario I believe most of you have encountered in your works as a data scientist. You have the data set, right? And you want to keep asking questions to the data set. In this case, I'm going to divide all the students that took the Sauerons exam and divide it in the nationality of each student. So we have high school students in Colombia, I'm going to divide them in students from country 1 to country N, for example, Colombia, Venezuela, students from the US. So divide the group into nationalities. The key here to remember is, despite each student is from a particular nationality, they're all from a higher group. All are high school students in Colombia. So notice a higher group, high school students in Colombia, particular groups, the nationality of each student. How can we approach this? We can either fit a linear model for each country, one for Colombia, one for Venezuela, one for Panama, and this is called the unpooled approach. What do we have here? N regressions, the number of countries, each one with a parameter beta I and alpha I. The other extreme of the approach is one linear model for all the data. That's basically what we did earlier in the example, one single regression for all the data. But we want kind of a Goldilocks approach. We want information from both the general case and the specific case. So what we do is calculate a beta I and alpha I for each country and center them around general beta and alpha. So notice this is great because we have information from both the group and information from specific countries. So you kind of have a general model and fine-tune it to each specific group. We will see the results from this approach, okay? So as before, I'm going to go quickly through this code. We define our priors, but this time we have two kinds of priors. The hyper priors, the ones for the general model, all students in Colombia. The specific priors are the ones for each country, okay? And as before, the likelihood is the same as the linear model. So this is what we get from these two approaches. In the left, we have the unpooled model, and these are two students in 2019 from the Netherlands took this Averronce, okay, just two students. And in the unpooled model, you notice there's a negative slope. We have a negative slope linear regression. And people from Netherlands may be different from us, but not that different. It's probably because there's not enough data to fill the model, but notice what happens in the hierarchical model. We follow the trend from the general group. Here I show in gray spots all the data from the group that is not Netherlands. And notice the difference between the two. And why is the difference? Because I'm passing the information from the general group to the specific group that is the Netherlands. So notice kind of the information from both ways. I'm fitting the model correctly in the right plot. I'm passing a good fit, but with the information from the general group. The more extreme case, only a single person from Panama took this Averronce. And how do you fit a line to a single point? You can draw any line through it, right? And that's why I'm showing you in the unpooled model. That's actually all the models, all the lines that the model is trying to fit through a single point. And that's what we would do if you're given a single point, right? Notice the difference between the unpooled model and the hierarchical model. Since I'm passing the information from the general group in the hierarchical model, we know which region of the space of the lines we can try for the model we're fitting. So notice in the left, we're completely lost about what to do. On the left, since we have information about the general group, we can restrict the region of the space we're using. Okay, so pretty powerful, as you can imagine, because as you ask questions to the data, you have groups with very little parameters, data points, sorry. So you want to keep using information from higher levels of your data. So yeah, that's the use of hierarchical models. The last example I wanted to show you, it's a behavior change example using probabilistic programming. So I was preparing the talk during Christmas, and I wanted to know if Colombians measure their family more during Christmas time in social media. Okay, this example, the idea for this example, I took it from a book called Bayesian Method for Hackers. It's a great book if you want to dive into the probabilistic programming world without much of the math. So that's our objective. How did I do it? I stored 10,000 tweets per day for November and December. Okay, so I have my data, the data from the real world, and I created a model to now model the number of tweets that include familia in the text. So that's family in Spanish. And I want to determine if the parameters of the model change in a day in December, right? So that would indicate that there was a behavior change in tweeting behavior. And also I want to determine when the model changed, okay? So we have here a diagram of the model I'm defining, and notice I am the one who's defining the model, right? I'm kind of in control of what the parameters of the model must be. So since I'm counting, I'm modeling counting data, I'm using the Poisson distribution, the appropriate distribution to model counts. And what I'm saying here is, I'm claiming before a time tau, that could be any day between November and December, I have a parameter lambda 1 for my model, okay? But in this time tau, the behavior of people change. And now my Poisson distribution is not governed by lambda 1, but it's now governed by lambda 2. So that's where we're going to find out, okay? And notice, 3 parameters for our model. So we have 3 parameters. We define our model again. This is again with PyMC3. We have 3 parameters. We define our priors for the model and our likelihood. Since we're using counting data, again, Poisson distribution. But how am I going to model this parameter change? And again, we're taking advantage of probabilistic programming. I'm defining a parameter switch, and since these lambda 1, lambda 2, and tau are distributions, but I can model them using Python objects. What I'm saying in this line is, if your day, for example, November 15, it's before my time tau, use lambda 1. If it's later, I don't know, December 31st, use lambda 2. Okay, so notice I'm modeling, I'm kind of writing the code for the model I was talking to you in the last slide. Okay, so that's as I told you, that's the key for probabilistic programming. You're the one who's defining the model. So here are the results. The lambda 1 is the posterior before the change, and lambda 2 is the posterior after the change, right? So notice, and we see no overlap between the 2 distributions, so we can conclude, in fact, that there was a behavior change in tweeting behavior. But what's more powerful about it, we can say, oh, there was a behavior change. Did people tweet more? Did people tweet less? Since I know what the parameters of my model mean, I can definitely say people tweet more. Why? Because as you can see, lambda 2 is greater than lambda 1. And since I know the lambda 2 defines the tweeting behavior after the change, I can definitely say at some point between November and December, people began to tweet more about their families. So notice the key here for interpretability. And that's the same case for tau. Since I know it represents a day between November and December, and here is the posterior distribution, it's pretty localized. I can say the tweeting behavior for people in Colombia changed between here December the 1st and December 11. In which day specifically? Around Dia de las Velitas. So for those of you who don't know, Dia de las Velitas is kind of the beginning of Christmas for us here in Colombia. It's kind of the beginning of the December holidays. So we can conclude with our model, we let the data speak for us and say, according to the model I defined with probabilistic programming, I can certainly say that Colombians tweet more about their families after Dia de las Velitas. And for us Colombians, that would make sense, because we think after December the 7th that it's family time, it's Christmas time. Okay? So notice the importance of model interpretability. I know exactly what's going on with my model. Okay? So just to conclude, I hope you learned with this talk what is probabilistic programming. Basically, it's a framework that allows us to work with random variables, and notice the power it gives us to define random variables. Which problems are best solved with probabilistic programming? Basically, when we want to include prior knowledge of our problem, and have intuitive uncertainty of our estimates. And also, I hope with the examples I show you, you know where to start with probabilistic programming for your own projects. So yeah, that's it. I hope you keep enjoying this amazing conference, and let me know if you want to know more about what we do at Factored. if you have an idea for your startup and you don't have the team to develop your AI idea, or you work in an organization that has an awesome AI team, but you need more hands to develop your product quickly, let me know. Here's my contact information, LinkedIn, email address, and it would be great also to talk to you in person. So now, if you have any questions about the talk, please go ahead. Thank you.